So, as we did last time, this is what we are going to do right now, the conduction abnormalities, and I'm going to summarize the important points of the conduction abnormalities. Basically, we started the last time the arrhythmias. We discussed the arrhythmia. What is arrhythmia? It's not a normal sinus rhythm. It can be different in rate or in rhythmicity or the impulse formation center. So this is one big chunk of the ECGs that we discussing. That was the impulse formation abnormalities. Now let's see in other topics when we are talking about a conduction abnormalities. So what does it mean? It's meaning the impulse is formed in the right place or maybe in different place, but after when we had a conducting pathways, somehow the conduction through those pathways is abnormal. So this is what we called, these are the blocks. And of course, if the impulse made somewhere, these should be propagated all over the muscles, all over the ventricles, and contract the heart. If we do have any kind of block, any kind of conduction abnormalities, for sure, the impulse is not propagated, the heart is not going to contract. This is what is making the arrhythmias. And in other areas, when we do have a faster conduction, usually we do have an accessory pathways, and that's going to give us, it's called the pre-excitation syndrome. But first, let's look at what we call as a block or conduction abnormalities. Now, generally talking, based on the severity of the block, we are talking about first degree, second degree, or complete block, as it's called, the third degree block. And by the location, as you see, we are talking about the sinoatrial block, the AV junctional block, and intraventricular blocks. Now, generally talking, what the first degree block means. The first degree block means that we do have connection between A and B point if you are evaluating the areas of the atrium or the ventricle or inside the ventricle or between the SA or in the atrium. These charge that made in one point that will propagate to the conducting pathways normally with a normal speed. So this is what the charge reaching B. First degree block means that we do have this connection. We do have a wiring between these 2 points, and this will work, but it takes longer time. So the conduction velocity is slowing down. That's a first degree block, what is so. So by meaning every charge that's made, it's propagated. So normal situation, this be rhythmic. First degree block, still rhythmic because every charge that made, it's getting to another area. So the heart works perfectly rhythmically, but takes longer time to get one point to another one. What the second degree block means? Second degree block means that we do have some block, complete block that is not conducted from A to B, such as, for example, as you see, the first is conducted normally, but the second one is not conducted. After we do have some conduction, after we don't have conduction. So this makes the heartbeat arrhythmic. This is the second degree. And the second degree AV block that you see, it has 2 different types based on the severity or based on the location. Now let's see. This is one is called Mobitz type 1. What does it mean? As you read it or you watch the movies, basically it's meaning that we do have conduction between A and B, but somehow this conduction is getting slower and slower by every revolution. And once the block is dropped, and after start everything from the beginning. So as you see here, the velocity of the conduction is slowing gradually, and one is complete block. And again, looks like there's a little rest is enough to the conducting area to be repolarized completely normally and start from the beginning and goes again. So it has some kind of rhythmicity inside this conduction abnormality. the second type of the Mobitz type 2. The previous one, as I saw here, this is called the Wenke-Bach periodicity as well, because it has some kind of periodicity. So these are two names, but I think it's enough if you remember Mobitz type 1 or Mobitz type 2. Now, Mobitz type 2 means that we do have conduction between A and B point, but the velocity of the conduction is not changing. So it was the same in the first one, the second one, the third one, but between these, we do have an unconducted block. By definition, the second degree block has only one unconducted bit between two conducted ones. So it's meaning that conducted, conducted, not conducted, conducted, that means second degree, okay? Or conducted, not conducted, 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 and not conducted. This is again a second degree block. Now, there's another type of the block that is a little bit different one, but it's difficult to distinguish between Mobitz type 1 and Mobitz type 2. This is a 2-to-1. What does it mean? It's meaning that every second bit is not conducted. So this is why the last and the first conducted bit the same. So we cannot say that the velocity is different or not. This is the 2-to-1, and you do see that it's bradycardic usually because every second one is not conducted. So this way, not every charge gets from one point to another one. This is the 2-to-1, and you have to compare. Now, why is it important, especially when we are talking about the AV block? The clinician should know whether this is a life-threatening situation or not. Mobitz type 2 is a life-threatening situation. And 2-to-1 again could be a life-threatening situation. So the physician is going to implant the pacemaker immediately into the system, especially when we are talking about later on the AV blocks. High degree block means that there are more than one unconducted bits we do have between two conducted ones. It's meaning that not conducted, not conducted, not conducted, and sometimes conducted. Now, this makes, again, this is rhythmic. So, first degree AV block is rhythmic. Second degree AV block, not rhythmic. 2-to-1 AV block is rhythmic. High degree is not rhythmic, because whenever we do have a conduction, that makes it arrhythmic. Because if we do not have conduction between 2 points, it's meaning that the lower center is taking over and you do have an escape rhythm. And once when we do have a conducted bit, that makes a little bit faster coming bit. Now, third degree blocks means that there is no connection between these 2 points. So not at all, forever. All right, this makes we do have a lower center if we had, and that's going an escape rhythm. Now, these kind of blocks could occur anywhere in the heart. Whenever we do have a pathways that conducting the charge normally. Of course, you know that we do have conduction between the nodal tissue and the atrium. These are between the A and B here in the SA node that we do have conduction. Or we do have conduction through the AV junction, and we do have conduction in the bundles inside the ventricle. Now, these are different blocks. We are talking about SA blocks, AV block, and intraventricular block. Now, one big problem, for example, in the SA block, we do not have any sign of the activation of the SA node. There is no sign on ECG. If you do have an esophageal ECG, or you place directly the electrode on the top of the heart or close to the assay, yes, you do see the spike when the assay is activated. Whatever you have only the ECG when the atrium is activated. So relatively, as you listen here, there's no sign of A, but we do see the P wave. So we have to diagnose this one based on the P's. The best one to look at the AV block, because we do see sign of the atrial activation, this is the A, and we do see the sign of the ventricular activation, that's the B, and we are evaluating the connection between these two, between the P and the QRS complexes. And intraventriculars, we are talking about the QRS shape and the width of the QRS, because that area that is has a block, that the charge goes through the muscle, so that has a muscle conduction. Now, AV block, let's go through because you already looked at it. Okay, this is incomplete when we do have the first degree, second degree, 2 to 1, and high degree as well, and the complete one, the third degree. This is how you can name them. Okay, let's see what the first degree. First degree is very simple one. We do have, you know that this is why we have to learn the different distance, the PQ interval or PR interval. This is from the beginning of the P till the beginning of the QRS complex, and that's the maximum is 0.2 seconds. And of course, this will depend on the heart rate. Because if you do have a faster heart rate, the PR interval is shorter. If you have bradycardia, the PR a little bit longer, but never ever exceeds the 0.2 seconds. So when we do have a first degree, every P gets to the QRS complex, every P followed by the QRS. However, the gap between the beginning of the P till the beginning of the QRS is longer than 0.2 seconds. This is what is called first degree AV block, and that's rhythmic. Keep in your mind that rhythmic. Okay, that's simple one. We will practice later on. We will practice. Okay, so as you see here, for example, that this is rhythmic. This is why we are starting the evaluation by looking at the rhythmicity. It will tell you a lot of things. For example, whether impulse formation or conduction abnormality or anything happening in the heart. Now, second degree AV block, that meaning that there are some P's that not followed by QRS. Very important. AV block, you have to have P and QRS. And you are evaluating the connection between these two. Okay? Mobis type 1, we said that the PR interval is getting longer and longer and longer. As you see here, what is going to happen? The PR is longer, but the P and the T distance is shortening, all right? And once that is reaching a very long way, P always inside, almost inside the T wave, that is a dropped P that's not followed by the QRS complex. Another very important one, that not only the PR is getting longer and longer and longer and longer, but as you see here, the RR interval is getting shorter. Now, this is not how you will recognize an second Mobis type 1 AV block, but it's very important when we're talking about the assay block, because we do have only in assay block the P wave. Now, if you had to diagnose, for example, the Mobis type AV type 1 AV block based on the RR or the only that you have a QRS complex, you have to evaluate how the RR is changing. Importantly, this distance, the last conducted and the first conducted R, the distance, is less than twice as the last RR interval. This you should keep in your mind. Now, this is what it's important one, and you already had this one, that's important point. But the P's, they coming regularly, okay? That's important, the P is coming regularly. However, you will find a P that is not followed by QRS complex. Another important one, the P's are identical, all right? This is another important point. Okay. Now, all right, let's go to the second degree. The second degree is very simple one because it's meaning that the P are always the same. However, you will find a P that is not followed by QRS. As you see here, the P equal. And when you do have the gap, when there's no QRS complex here, this is exactly twice as much as the last RR interval. That's simple. 2 to 1 AV block, very simple. Every second P is not conducted. Okay, you can see P's, however, you do see some dropped P's. You should I should mention that the T is bigger than a P wave. And if you do have QRS, you have to have T wave. Don't forget it, because sometimes when we were talking about some uh, impulse formation abnormalities, and sometimes it could be you assuming that, oh, that's T should be the P wave. No, T has to be if you have QRS, and an additional wave should be the P wave that is smaller and is distinct for the T wave. Okay, that's a bradycardic, as you see, and always you do have P wave that the shape is the same. High degree blocks. Now, that's a little bit difficult to understand. First of all, most of the time, or some segment of this ECG is rhythmic. Because if we do not have conduction between these 2 points, it's meaning that the ventricle cannot be contracted. However, we do have, let's see, a system that is saving our life, and that's the nodal tissue in the lower part of the AV or inside the ventricle that's generating the own impulse. However, the rate should be less, much less, and that means that's rhythmic. So we do have escape beats, okay? And whenever a supraventricular conduction occurs, as you see here, we do have a relatively normal QRS complex, but this is arrhythmic. And this is what is called capture beat. So the capture beat is always arrhythmic, so it doesn't come in the time as an escape rhythm. However, it could happen that the supraventricular conduction and the escape bit from the ventricle hitting the same time of the ventricle. So it's meaning that some part of the ventricle was activated through the normal conducting system from a supraventricular source, and some part was activated through the escape center. So this is what is called the fusion bit. So if you are looking at a high degree block, first of all, is arrhythmic, and you do see at least 3 types of QRS complexes. One type, that's an escape bit. Another type, the capture bit, it's coming from supraventricular area. And another one, in between these two, some kind of, it's called the fusion bit. So it's not the same as an escape bit because it's altered by a normal conducting pathways activated ventricular pattern. Third degree blocks, very simple one. It's rhythmic. How can you judge it? Basically, you do see P waves and the P is coming in time, all right? However, there is no connection between P and QRS complex. You could assume that maybe the PR distance is changing and okay, it is getting longer and longer and longer, and after it's not conducted because somehow, yeah, but this is arrhythmic completely, and the RR interval constant. Maybe you could confuse with Mobis type 1, but in Mobis type 1, the RR intervals are not constant. And another thing, that basically the QRS complex is normal in Mobis type 1 AV block, because that's meaning the AV, when conducted, is reaching the bundles and giving a normal QRS shape. But here, these RR intervals are constant, and you do see very nice wide QRS complexes. It could happen that this escape center is very close to the lower part of the AV junction, and this way the QRS complex is not as wide as not a typical one as a QRS complex of the ventricular origin, but is still you do not have any connection between the P's or in the P and a QRS complex. Sometimes it's happening that, and this is another good clue, that the PR is getting shorter. Okay, the PR is getting shorter. If you do see this feeling that the PR is getting shorter and it's rhythmic, for sure is a third degree AV block. Okay, so we do have P waves and we do have a normally rhythmic QRS complexes, and that's the third degree AV block. As you see here, we do see rhythmicity, but of course, we do have a lot of P's. That is a simple one. Third degree, okay, we will solve. Now, essay block, that's a little bit difficult one. And that could be the first sign, for example, of oxygenation abnormality when the SA block occurs. Now, that meaning that we do have still first degree, second degree, and Mobius type or Mobius type, and a third degree. Now, first of all, you cannot recognize the first degree block because first degree block means that it's getting out and is getting out rhythmically, so there is no sign of on or 12 leads ECG. There is no sign. If you had an esophageal ECG and you can detect when the assay is activated and after the charge is propagated and how fast the charge propagates to the the atrium, that could be a very good clue. Now, second degree, a little bit difficult one because it's meaning that there are missing P waves. That's be very similar when we had an impulse formation abnormality. It's called the sinus arrest, when there is no impulse made by the SA node. The difference between sinus arrest and first degree or third degree SA block, that meaning that in this situation, we do have a nodal impulse formation. However, the charge is not getting out from this assay. Now, again, that's not an easy to diagnose. Basically, from the arrest or complete stop of the assay, especially when we are talking about the third degree assay block, because there is no P wave and only we do have a junctional escape rhythm. Now, in case of the first degree assay block, not the first degree, the second degree, but Mobius type or Mobius type 2, we have to evaluate the PP distance because normally the PP interval are constant. Here, however, is not. For example, looking at this charge, you do see a P here, but there's no P here, okay? And after you do have a P wave, and P wave, and P wave, and P. Now, what you have to do, basically, let's look at the last conducted piece and the first conducted piece, and looking at whether this twice as much or not, that's this when you do see the PP interval. If this distance is shorter than the last PP interval, it means Mobius type 1. If the distance are equal, that's called Mobius type 2. Do not worry because I do not think that during the midterm you will face this kind of ECGs. It's not an easy to diagnose. You have to have a good practice to diagnose this one. Okay, and you watch the movie, so you don't need to watch it right here. Now, as you see here, of course, assay block, the first degree is arrhythmic as well. And what we have to do that basically you have to looking at the PP interval and comparing that to this one. Okay. Second degree Mobius type 2. Very good. Okay, good. Go on. Now, the next big chunk of this conduction abnormalities, this is the bundle branch blocks. A lot of time you will face with these bundle branch blocks. And of course, you know that the bundles anatomically, that is when it's going from the bundle of His and very early, it's going to has a fascicles such as a right branch. And we do have another one that is septical fascicles. And we do, this is the left one, okay, this is all of them, it's a left bundle. And we do have the anterior and the posterior part of the left bundle branch. And of course, any of these fascicles can be blocked. So this is what we are talking about. For example, right bundle branch block, when the right bundle is not conducting. Usually we're talking about a third degree right bundle branch block because none of them is conducted. But sometimes it could happen that sometimes the QRS is normal, but sometimes gives you the right bundle branch picture, and that's meaning that's not a complete right bundle branch block. This kind of bundle branch block could be rate dependent, so heart rate dependent, because if the rate is fasting, relatively you do have less time for the repolarization, and the bundles are very sensitive to oxygenation, and usually this is what we are going to see immediately. The left bundle branch block, when we do have relatively, it's blocking the complete one, is blocking out completely everything, including the septal part and the anterior and posterior. But it could happen that this block occurs maybe only and affecting the anterior fascicles or the posterior fascicles. We're talking about bifascicular block. So far we had the right and the left can be anterior or posterior. These are the hemiblocks. We can have bifascicular when at least two fascicles are affected. The right bundle always included. So the right is out and or the left anterior or the posterior is blocked. We can have trifascicular block. Trifascicular block usually is meaning that we do have a right bundle branch block, we do have an anterior or posterior hemiblock, and we do have a first degree AV block. These are all caused by ischemia or infarction. This is what we have. Now let's go and summarize how the ventricle is activated normally. First of all, we learned that the septum is activated from the left bundle. All right, from the left bundle. If you are looking at, for example, here, this is the septal fascicle, the charge about 90% coming from the left bundles. All right, that's important. Okay, and that's give us a little positive wave, a little initial R in V1, and a negative wave, a Q wave on the left side in V6. Next one, the right and the left side activated simultaneously. However, because the left ventricle is about two and a half times thicker than the right one, and electric activity about 10 times higher than the right one, this is why the vector of the ventricle activation vector is pointing toward the left side. So this is why you do have a big R wave in the left side and the deep S wave on the right side. So what you do see here, an RS in the V1 and QR in the left side. Okay. Now, we do have another terminology, the intrinsicoid deflection or ventricle activation time is synonym, the same. Its meaning then from the beginning of the QRS complex till the last R wave, okay, or the biggest of the last R waves. This is different in each lead. This is why we should look at in right side and left side. Or right side is very, very teeny tiny one because this little initial R is only the septal activation. So it's less than 0.04 seconds, so it's meaning less than 1 millimeter. However, on the left side, because it's considering the top of the R wave is less than 0.06 seconds. That's be important because whenever we do have a block, that those part of the ventricle activated later. So the left ventricle activation time is elongated, means we do have a left bundle branch block. If we do have the right side, the ventricle activation time elongated, that means we have a right bundle branch block. Okay, let's see what the right bundle branch block means. Okay, the first part of the septal activation is normal, so relatively we do have initial R wave in V1, we do have a Q wave in V6. The left ventricle activation is completely normal, fine, that's good. So the first part of the RS is okay, or the QR is okay. Now, what will happen with the right side? It's activated later and through the muscle. This is why we do have a wider part of this activation. It's meaning that we do have a wide R wave in V1 and a deep S wave on the left side. So this is why the pattern is RSR pattern, but sometimes it's not an RSR pattern, only a notched R. But as you see here, the ventricle activation time or the ID time is elongated on the right side and not influenced on the left side. Okay. I don't want to talk too much about the very simple one, very simple, and you can diagnose it by looking at, for example, the V1 or looking at the left side, lead number 1 or V6. You do see that very slurred and wide S wave on the left side and a tall R wave in V1, for example. Now, I haven't said anything about the complete and incomplete, only the matter of the width of the QRS complex. If the QRS complex is still in the normal range, this is called incomplete block. If it's wider than 0.1 second, that's called complete block, bundle branch block. Okay, yeah, this is what I said. Okay, now let's see the left bundle branch block. Septal activation influenced, yes, because a septum can be activated only from the right side. This is why you do have a S wave in V1 and the R wave starting in the left side. And of course, after we do have a impulse that goes from later on the right to the left. Sometimes you do see a little notching in this one because the right bundle activates the right ventricle, but sometimes you do see nothing. And of course, the left ventricle activation gives you a wide, big R wave on the left side and a deep S wave on the right side. So the left side, we do have a wide R and a negative or the S wave in the right side. As you see here, the ID time or the ventricle activation time is not altered because less than 1 millimeter. However, on the left side, yes, that has a pattern. It looks like as a M. Whenever you do have a block on that side, we do have this a notched R wave or M complex. This is why sometimes you can see some books that saying that William, for example, for the left bundle branch block. And if I go back to the right one, this is called Morrow because that should be an M and that should be a W. Oh, well, if you can recognize that a W. Okay, go on. Looks like everything that we do have a wide QRS looks like as a ventricle rhythm. But first of all, how can we judge whether it's ventricle rhythm or not? We do have P wave and we do have connection between P and the QRS complex. And of course, the ST segment is altered and that will cause some secondary ST changes. Any kind of muscle conduction is altering the repolarization phase, the STT segment. So you have to judge it. When we are talking about ischemia, you have to separate from the conduction abnormality altered STT segment or the ischemia caused STT alteration. Okay, anterior and posterior hemiblock. Now that's relatively, how can we diagnose? If we do have a hemiblock, the width of the QRS is not altered. However, what is altered? The electrical axis, the main electrical axis. This is why we are calculating the axis. Very simple. Anterior hemiblock will cause a extreme left deviation because the anterior part of this fascicle can be activated only from posterior. And the posterior fascicles is running from, let's see, to the right, to the left, and on the back of the ventricle. So this way, the all charge coming from the right to the left. This is why we do have a pathological left deviation. All right, looking at this one positive, AVF negative, two negative, that's a hemiblock, that's a extreme left deviation. The posterior, exactly the opposite, because the anterior gives us the charge toward the right side, so that will give us an extreme right deviation. That's it, period. Only looking at the axis, one is negative, immediately you can say that possible, that's a pathological right deviation, all right? You are not making a mistake. If you're looking at AVR, it's still negative, so it's between relatively 100 and 120, so it's less than 120, but possible that's a hemiblock, the sign of hemiblock. Now, when we're talking about bifascicular block, we do have the typical pattern of the right bundle branch block, okay? You do see that the ventricle activation time or the M complex occurs in the V1. Or sometimes you do see this kind of notching R waves in V1 or right side or V2. And the axis is extreme left deviated. So this is what we call as a bifascicular block. Okay, similarly, typical sign, as you see here in V1, typical sign of the right bundle branch block. The last sign, the last part of the S wave is very wide in lead number 1. Okay, good. So that's a right bundle branch block. And the axis, one is negative, so there's a posterior hemiblock. This is what is called bifascicular block. Good. Trifascicular block. The trifascicular block can be a lot of things. One thing, as already mentioned, that right bundle plus the left anterior hemiblock and the first degree AV block. Right bundle branch block together with the left posterior hemiblock and first degree AV block. Or both one is out, left posterior and anterior is out, and we do have a first degree AV block. Or we do have an alternating of the right bundle with the left bundle branch block. This can happen. So these are all called a trifascicular block, but the easiest to diagnose that we do have a right bundle branch block, hemiblock, and a first degree AV block. Okay, this is we will have in later on. But as you see here, yes, we do have a right bundle branch block. We do have a pathological left deviation, anterior hemiblock. And if you are looking at the PR interval, it's getting longer than 0.2 seconds. So this is why it's a trifascicular block. Okay. Now, rate-dependent right bundle branch block, as I mentioned, that when we do have tachycardia, the right bundle picture occurs. So this is not a complete right bundle branch block. That can be the high degree or uh, second degree, but it's called the rate-dependent right bundle branch block. Now, let's see something about the pre-excitation syndrome. The pre-excitation syndrome meaning that we do have a faster activation. Okay, we do have only one part when we do have a slowing down of the conduction, and that's the AV node. So we do have an accessory pathways, and that bypassing the AV node, and that can be a lot of things, but we do have only two types, the WPW syndrome or LGL. We do have the CAND bundle. This is a muscle type bundle that is connecting the atrial muscle to the ventricular muscle. And of course, the ventricle activation or a conduction is faster than an AV conduction. This is why the charge getting faster to the ventricle. And another one, the James fiber, when it's going from the atrial muscle to the bundle of His, directly to the bundle of His. This is being a different one, and that's give you a different ECG sign. Okay, let's see the WPW syndrome when we do have a CAND bundle. Fine, that's a muscle type bundle. What will happen? The SA activates the atrium. Good. That we do have the P wave. Now, the charge normally gets to the AV node or the bundle of CAN. But what will happen in the AV? We do have a slow conduction, all very slowly going on the conduction. However, a bundle of CAN, as a muscle type, immediately starts to activate the ventricular muscle. This is why that's a dotted line means that the AV conducting charge, and the blue one, that a muscle type conduction. What you do see, the PR is short. Right after the P, a ventricle activation starting. So the QRS is getting wider. And the first part of the QRS looks like as a delta wave, as you do have. So this is the sign of the WPW syndrome. Similar, simple one, PR is short, and we do have a wide QRS. PR is short, wide QRS, WPW syndrome. That is a really frequently occurring abnormality, and sometimes doesn't cause any problem, but sometimes it can cause some kind of paroxysmal tachycardia, or especially when we have flutter or fibrillation, that can kill the patient later on. So that could be very important one. Now, there are two types of this WPW syndrome depending on or the right side or left side. We do have this bundle of CAN. It can be anywhere. And of course, they will determine precisely because what they can do, one, nothing, another can catheterize, so they can remove or they can cut this bundle if the patient has some problem with it. How can we diagnose A type or B type? Look at V1. If it's a positive one, the delta start positively, that's an A type. If it start negatively, that's a B type. Looks like that's similar to the right bundle, that's an A type. And when we do have this left bundle, that's a B type. Okay, that's nothing else. Okay, so that's an A type, that's a B type, good. LGS syndrome, nothing at all, only what you do see, the PR is short and the QRS is narrow. That's it, LGS syndrome. Okay, pre-excitation syndrome, or that is meaning that can cause tachycardias. Now, we do have, we already discussed this one when we had a paroxysmal supraventricular tachycardia, nodal tachycardias. Now, very commonly, that's accessory pathways can cause tachycardia. This is what is called re-entry tachycardias or AVRT tachycardias. Now, AVRT tachycardias meaning that we do have this re-entry phenomenon that develops this in atrium and the ventricle, and of course, these accessory pathways can serve to maintain this impulse formation or impulse formation. Now, how can we differentiate between? First of all, if you apply, if you increase the vagal tone, carotis massage or Valsalva maneuver, this will stop immediately this kind of tachycardias. Patient will know it and they will stop immediately. Now, there are two types depending on the function of the bundle of Kent. If the bundle of Kent reuptaking the charge only, so the ventricle activated through the normal conducting pathways, this is called orthodromic AVRT tachycardias, so the QRS is completely narrow, or the antidromic one, this is called when we do have a wide QRS tachycardias because the ventricle activated through the muscles and AV junction reuptaking the charge only. So the AVRT is a narrow, orthodromic, or antidromic. This is what is called this AVRT tachycardias. For example, the orthodromic, as you see here, very narrow QRS, and you do have a wide QRS. This is called the antidromic AVRTs. Now is another one, but the nodal tachycardia, this is so-called AVNRT tachycardias, when this reentry developing inside the AV node or AV junction, and that's be very fast. And of course, this is paroxysmal, the reentry tachycardias, mostly paroxysmal tachycardias, and the involving only the AV nodal one, and very frequently can occur, and this is the most common cause of the regular supraventricular tachycardias. This is the AV and RT tachycardias. Okay, this is what I wanted to summarize this one. Okay, so let's start the tracing. So 104. Whoever is not here, I will do it. Okay, so let's see. First of all, we have to look at the rhythmicity. This is rhythmic, fine. The heart rate is around 100, a little bit less than 100, so we can say 90. That's fine, period. The next one we have to look at, what we learned, that do we have P wave? Yes, we do have P waves, and the P's are coming regularly. All right, so that's fine. So we do have sinus written because the P wave is positive in lead number 2 and negative in AVR, and they look the same in shape. Good, period. Next one, we said that the axis, this is what we learned so far. Lead number 1, it's close to 0, but I would say that's a little bit positive. Okay, AVF is positive, so we have to assume that this is normal. Because lead number 1 is almost 0, we have to assume that this is close to 90 degrees. The less than 90 degrees, so I would say about 80 degrees. This should be the main electrical axis. Next one. All right, the morphology of the P wave. This is about 0.1 second, that's fine, the duration. And the amplitude is around 2 millimeters, that's fine. So there is no any sign of atrial hypertrophy. This is what we are learning later on. Now the next one about the PR interval. From the beginning of the P wave till the beginning of the QRS. And if you look, that should not be larger than 0.2 seconds. As I see here, that's longer than 0.2 seconds. So we are assuming that this is a first degree AV block. Importantly, this is rhythmic. This is why you can say that first degree and every P conducted. Okay. Let's move on. Okay, let's move on. And okay, I'm checking the next one. I think 103, right? Is not here, I think. No, is not here. Okay, Louis is not. Wait a minute. I'm checking. Louis. Yes, Louis is here. Okay, who is here?
I'm here.
I'm here as well.
Okay, whoever can share the screen, I'm more than happy to see it. Okay. Uh,
I have my tracings on my iPad, but I'm on my laptop for the Zoom. So if you could share the screen for mine, that would be helpful.
okay, Sebastian, let's look at which one that you had. 109, yes, 109.
Yeah, yeah, 109.
Okay, 109. I'm going to go there. 109. Yes. Okay, it's your turn.
So what I see is a rhythmic but bradycardic rhythm. Uh,
Mm-hmm.
I say the heart rate is about 40 beats per minute.
Mm-hmm.
And because we see P waves, but only every second P wave is conducted, I said that this is
First of all, as you see here, this is only one lead. Okay, this is lead number two, and this is a consequently recorded tracings. Okay, it's not
yeah.
parallel recorded. That's very good. So now, one thing that you mentioned is rhythmic. Okay, I assume that you are right. Okay, let's look at, we do have P waves. Okay, that's correct. Okay, we do have P wave. And it looks like then we do have a P, that this piece comes every secondly be conducted. Okay, it looks
Yeah,
like.
that's what I said.
However, if you continue looking at this piece, okay, you can see that, for example, I'm going okay, this, this should be somewhere here. This should be somewhere here. All right. So it looks like that this PR interval is not constant.
Hmm.
Yes.
Okay.
If you had a 2 to 1, the conducted PR should be constant. But because this PR is not constant and is still rhythmic, okay, it cannot be a 2 to 1 AV block.
Oh, okay. Well then, I guess if it's a regularity in terms of the R to R, then it
Uh-huh.
must be not a supraventricular rhythm, but a sort of escape because the P and
Very good.
yeah.
Very good.
Okay.
Very good. So it has to be an escape rhythm, and this is a complete AV block. And that, let's see, this escape rhythm is originated from the low part of the uh, junction. Okay. So looks like this is a, let's see, the AV node, this is a bundle of his. Maybe somehow we do have a block right here, and the pacemaker is still in another tissue, but none of the piece and cannot go enter back to over the atrium. So it's meaning that's a junctional escape rhythm with a third degree of AV block. Okay? Good. This is why you have to go all the way to the P's and looking at the connection between P and the QRS complex. All right?
Sorry, could you repeat how you found that it was a junctional escape and not a ventric? Oh, is it
Because,
because the
okay,
QRS is narrow?
correct.
Ah, I
Yes.
see.
Plus,
Okay.
not only the QRS is narrow, but if you look at the T wave is the same direction as the QRS complex. All right. So
Okay.
it's meaning that the ventricle activation was taking place through the bundled and the repolarization takes normally. Okay.
Okay. Thank you.
All right. Good. Who is the next one?
Also, I have 107.
Mizuho. Okay.
Yeah.
I will share my screen, or do you want to share it?
Yeah, I can show it.
Okay, I stopped sharing it and your turn. Oops. Yes.
Well, it is rhythmic,
Okay.
and heart rate is about 46,
Mm-hmm.
and it is second degree AV block, and it's 2 to 1 AV
Okay.
blocks because every second period is not conducted, and
Okay.
all
Now,
the
okay, I'm sorry. So you can find the P's that coming regularly. That's okay. That's correct.
uh-huh.
And now if you are looking at the PR distance, these are constant. So whenever the P is conducted, the P are the same. Okay. And this is how you can mention that this is a 2 to 1 AV block. Okay, go on.
and also all the RR
Mm-hmm.
are the same,
Mm-hmm.
and yeah, and the axis is minus 30 degree,
Mm-hmm.
because the most equivalent one is the second lead, and LVL is positive,
Mm-hmm.
so I chose minus 30 degree.
Okay, a little, if you are looking at lead number 2 is still positive, a little bit still positive, yes?
Mhm.
Okay, and this is why I would say that this is more likely that is less, or let's see, less than minus 30. Okay,
Mm, okay.
all right, and that's it. Okay, good. All right. Next one, who is here? Let's see, I'm looking at Luyain, 105. Are you here? No, not here. Okay, Prasant. Okay, Mizuho is here, but I think you don't have a microphone.
No,
She's the one.
I just did it. Yeah.
Okay, yes, you did it right now.
Yeah.
Okay, good. Thank you, thank you, thank you. 109 is okay. Who has the next one? Okay, Dong Young.
Yes.
All right, can you share your screen?
I'm sorry, would you share your screen, please?
Okay, first I have to find out which one that you have, which is the tracing that you have.
I have 122.
1 and 22. Okay, right. Okay, 122. It's coming up. 122 is coming up. Okay, great. It's right here. Okay, good.
I thought this is the ST elevation myocardial
Da,
infarction.
da, 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 da. Step by step.
Okay.
Rhythmic or not?
Uh, for me, I thought it is not arrhythmic.
Okay, it's not rhythmic. You can see here, this is not at all. You don't have any rhythmicity. Very good. Next question right away. Do we have a P wave?
Do we have a
Can
P
you?
wave?
Hmm?
Yeah, at the second let number 2,
No
I
way.
think.
This is
No.
what I said. This is T wave. That's T wave. If you do have QRS complex, you have to have a T wave. Okay. This is not.
Um,
So there is no P wave. What does it mean? Arrhythmia, no P wave.
um, sorry, could you tell me the answer, please?
arrhythmia, no P wave. This is atrial fibrillation, okay? Atrial fibrillation. Do not forget it. Because,
Atrial fibrillation.
yeah, because if we do not have P's and we do have rhythmicity, we have to assume that we do have an escape rhythm, such as a nodal one, such as a ventricular one. But that's rhythmic. If it's arrhythmic and we do have different P waves, that means we do have a multi-atrial or tachycardia or impulse formation. If we do have arrhythmia absoluta with sinus P wave, that's a 6-sinus syndrome. This is what we discussed the last time. Okay. Now, we do have atrial fibrillation. It's meaning that the impulse made by the atrium. So that's a supraventricular impulse formation. Next is the QRS, because you don't have PR intervals. You don't need to consider the PR interval. Looking at the, as you see here, for example, looking at the QRS complex, the next one, you have to look at the width of the QRS. And as you see here, the QRS is wide. What does it mean when we do have this supraventricular impulse formation and the QRS is wide? We do have an intraventricular conduction abnormality. What we have to do? First, we have to look at lead V1 or V5 or lead number 1. So we have to look at the right side and the left side. Left side can be V6 or V5 as well. And whenever you do have the ventricle activation time is elongated, the block is there. But it's a typical one. This is a RSR pattern, okay? This is the M phenomenon. So that's a right bundle branch block, okay? So we do have a right bundle branch block. Okay, axis. Lead number 1 is positive. AVF is positive, so that's normal. If lead number 3 is almost equiphasic, so this is close to 30, okay? So the axis is around 30. Correct?
Professor, I thought it was like almost more close to 50. Could you explain how did you calculate the 30 degree?
Okay, that's simple. Let's see. First, I looked at lead number 1. Lead number 1 was positive, okay? That's meaning we are on the left side, okay? We are on the left side. Good. Next one, we looked at AVF. AVF is positive, okay, all the way down. So we are somewhere here between 0 and 90 degrees, all right?
Yes.
Next one, I looked at lead number 3. Lead number 3 is perpendicular to 30. And lead number 3, this is what I said, it's almost 0, yes? Positivity and negativity are about the same. This is why I said this should be 0. Okay? All right. Good. Let's see. Who is the next one?
I have C1 to 3.
C1.
1, 2, 3. I think it's the next one.
Okay, 123. Okay, one. Next one. Let's see. Okay, I'm going. Oops. 123. Yes.
Yes.
Okay. It's your turn.
I think based on the continuation of lead 2, it's not non-rhythmic. So I counted that there are 11 beats in 10 seconds, which is around 66 beats per minute.
Mm-hmm.
I recognize QRS complexes in lead 2 and 3.
Mm-hmm.
And they each have a P wave.
Mm-hmm.
And I tried to estimate the distance between the P and R, and it was
Mm-hmm.
less than 0.2 seconds. So I think there is no AV block visible on the CC
Very
case.
good. Very good.
But otherwise, I'm not sure what conclusion to.
Okay, no problem. Whenever we do have a gap. See, it's a long gap.
Mm-hmm.
There is no P. Okay? There is
Mm-hmm.
no P wave.
Mm-hmm.
Okay? But other we have, there is no P. It's missing the P. Okay?
Uh-huh.
So it has to be an SA block.
Right.
Okay?
Okay.
Because there's no P, no QRS. Okay, fine. What we have to do, basically, we have to count how many, let's see, square we had between this P. I will count it 1, 2, 3, 4, 5, 6, 7.5. Okay, 7.5 square. Okay, 7.5 square. Yes? Okay. How much is this one? That's okay. I would say 1, 2, 3, 4. Okay.
Mm-hmm.
This is the last conducted PP. Okay. That means 4. And taking twice this, that should be 8. Okay. Meaning that this distance is less than twice as the last one. So we do have a Mobitz type 1 assay block.
Uh-huh.
Okay.
Okay.
When
Yes.
we're talking about AV block, we do have P, and we see that there is no QRS behind the P. But because we
Right.
have an assay block, we have no P, because the charge is not getting out from the sinus. Of course, this be similar to the sinus arrest, yes? However, in case of the sinus arrest, that distance should be twice as much as the PP interval. Okay, because only one revolution is missing. Almost impossible to recognize the difference between the assay block and the sinus arrest, okay? Except that sinus arrest usually come randomly, while this Mobitz type 1 assay block types comes regularly. Okay, good. Now, who is the next one?
I can go.
Joshi.
Yes, number 119.
119. Okay. Yes, I'm going there. How much was that? 119. We have to go back. Yes. 119. Ah, yes. Okay, good.
Yeah, so it appears rhythmic.
Okay.
The heart rate is around 100.
Okay.
If I calculate the electrical axis, it would be if I look at lead 2, it's the most equiphasic looking, and ABL is positive, so it's around -30.
Okay. Exactly. -30. Good.
P
So that's an
waves,
extreme left deviation. That's an extreme left deviation. Okay.
yeah. P waves are present
Mm-hmm.
and they're
And comes
consistently
regularly.
there.
Okay. Good.
So normal sinus rhythm.
Okay.
And um I can the PR interval is also constant, but I think the QRS is a bit wider.
Not a little bit. It's wide.
Yeah,
Okay.
the QRS is wide and
Mm-hmm.
the R peak is quite tall in the V1.
Mm-hmm.
So I would say maybe the right bundle branch block.
Lead number 1 is a left ventricle lead. Okay. That's a left ventricle lead. V1 is a right ventricle lead, right?
Yeah.
So it looks like the charge goes from the right to the left. Okay.
Okay.
What did I say? How can you recognize right bundle branch block or left bundle branch block? Whenever you do have the wide R wave, the block is there. Where do you have the I wave? Left side. So that's a left bundle branch block. Okay?
Okay.
And you have a pathological left deviation, but this can be due to left bundle branch block. So left bundle branch block itself can cause extreme left deviation. All right?
Yeah. Okay.
Okay, good. Let's move on and clear or
I have
drawing.
I had 114.
Okay. 114. Okay. Yes, I have to go to 114. Okay. Yep. All right. That's it. 114.
So at first glance, I think it's rhythmic,
Mm-hmm.
and there are four beats in 6 seconds, so it's 40 beats per minute.
Mm-hmm.
And looking at the P waves, I see that every second wave is conducted, meaning that is 2 to 1 AV block.
Okay. Very good. Now that's a 2 to 1. And this, you see that these conducted P are the same. Does not matter whether this PR is longer than 0.2. Doesn't matter. But this conducted. And every second conducted, this is 2 to 1. Okay. All right. Go on.
For the axis, I'm not really sure because we cannot see AVR, but I see
Doesn't
that
matter. Look at this. This is lead number 1. It looks like changing.
yeah,
Why the QRS is changing? Why the axis is changing in lead number 1?
right axis deviation.
No, well, or exactly perpendicular to lead number 1, so it's close to 90. Okay. I
Okay.
believe maybe it's 100, maybe it's only 90, but when the patient taking the breath and down and up, this is how the diaphragm is altering the mechanical axis. Okay, but for sure that's very difficult to determine what could be the axis. And as you see here, 2 and 3 is not the same. 3 a little bit bigger one, so you are right, a little bit more than 90 for sure. But we don't know whether this is 100 or over 100. Okay, good. All right, next one.
I have 134.
Oh, it's okay. All right, sure. 130.
4.
134.
But yes.
134. I cannot see it. What did I? 134.
Yes.
Okay, let's go. 134. All right. Maybe I have to go faster. Okay, that's 134. Good. A little bit smaller. Wait a minute. I tried to make it smaller. Okay, good.
So it's rhythmic,
Mm-hmm.
and the heart rate is about 120 beats per minute, and it's
Mm-hmm.
with tachy. The axis is about 70 degrees. The lead one is negative, and 2 and 3 are the largest, and the
Mm-hmm.
AVF is also positive, so it's approximately around 70. The P wave is present.
70. What do you mean 70?
70 degrees.
One is negative, okay? One is negative.
Yes.
It cannot be positive. It cannot be on the left side, I mean. AVF is positive, it's okay. But what does it mean? It's meaning that you are on the right side, yes? And AVR is negative because that's a QRS complex is negative. So it's meaning that you are between 90 and 120.
Mhm.
Yes?
Oh, so it's 110 or 100.
Yes, it's okay. 110, 100 doesn't matter. Go on.
We have P wave, which is
Mm-hmm.
looks normal, and followed by a QRS, and
Mm-hmm.
the PR also is constant, but
And
the QRS is wide.
no. PR is constant, but the PR is wide,
Wide, yes.
longer than normal. It's longer than 0.2 second. That's period. Okay, make your note. What
As
about the QRS complex? Is wide, you said?
it's also prolonged, and
Yes.
we have a M shape on the lead one and V3, which I think it's left bundle branch, right?
V1 is positive. What did I say? Whenever you do have the wide R complex, the block is there. That's the right side, okay? That's the right side. This is the left side, okay? Here you have a deep and wide S wave. See? Deep and wide S wave, okay? Yes?
So
So this is
it's
a
right bundle branch.
Correct.
Blah, blah,
Right
blah.
bundle branch block. Okay. And we do see a right axis deviation. That's meaning left posterior hemiblock. Okay. Plus we have a first degree AV block. How would you call this?
So it's trifascicular.
Correct. That's a trifascicular block. Trifascicular block. Very good. Trifascicular block. Good.
Sorry,
So we
could
do
you
have, yes,
go through how you got the other two as well? Because I see the right bundle branch block, but the other
good.
two
All
are just
right. Now I am happy that at least you recognize the right bundle branch block. How did I get to the left posterior heavy block? Axis. That's an extreme right deviation. And when we do have an extreme right deviation, that's a left posterior hemiblock. When we do have an extreme left deviation, that can be a left anterior hemiblock. This is why we are going to calculate the main electrical axis. Only this is how we can recognize a hemiblock. So far we have two right bundle branch block and a left posterior hemiblock. So far we do have a bifascicular block. Yes, but because we do have a first degree AV block, yes, that makes three.
okay.
Yes?
That makes sense. Okay. Thank
Okay,
you.
good. All right, let's see the next one. Who has the next one? Or anybody?
I think I can go with
Anna,
C 129.
129, okay. Yes,
I
129.
think, yes, one more. Yeah, that one.
Okay.
So I think this graph is rhythmic.
This is rhythmic.
It's not.
That's distance, and that distance, and this distance, and this
Okay.
distance. I don't think that they are the same. This is arrhythmic.
Arrhythmic, okay.
Mm-hmm.
It was hard to see, but P wave, I thought there.
Almost, okay, look at lead number 2. There's no P wave. It's not a nice run shaped P wave. Good. If you look at V1, you do see a very fast wave that the rate, look at the rate. It's very fast.
Fast, yes.
It's more than 350. What does it mean?
Tachycardia.
No. What does it mean when the atrium has a rate of between 350 and 600?
Bundle branch block.
No, nothing to do with the P wave or atrial impulse formation. That's atrial fibrillation. How can we recognize atrial fibrillation? I said it's very, very important. First of all, arrhythmia absoluta, no P wave. Or if you do have some kind of noisy background and the rate of this contraction is faster than 350, that's atrial fibrillation. And this makes the heart rate arrhythmic. Okay?
Okay.
Now, go on. We don't need to talk about the PR interval. We have to talk about the QRS complex. Is it wide?
Yes.
Okay.
So
Now we know that we do have a supraventricular impulse formation and we do have a wide QRS. What does it mean?
So
So we do have a supraventricular impulse formation and with a wide QRS, what does it mean?
it has a bundle block.
Bundle branch block. Which one?
Left side?
Yes. Lead number 1, as you see, nudged R wave, okay, or wide R wave in V6, V5, and QS complex in V1. So that's a left bundle branch block plus an atrial fibrillation. Okay?
Yeah.
Good. Wait a minute. Good. All right. Now, Go on. Who is next one?
I have 127, sir.
127. Yes, 127. Okay, I'm sorry. 127 is right here. Okay, good.
Looking at the rhythm strip, it looked rhythmic for me.
Mm-hmm.
And the R2R distance was a bit more than 5 boxes, so I measured around 57 beats per minute.
Mm-hmm.
And looking at lead 1 and 2, we can see P waves present.
Mm-hmm.
I was kind of confused with the axis because lead
No.
1 was definitely positive, but AVF, I wasn't sure how to determine such a flat.
Zero.
A zero.
Zero. What does it mean? What does it mean? The
You
axis
mean
is
perpendicular?
exactly 0 degrees. That's okay. Good. Okay, go on.
And for the conditions, I looked at the V1 lead, and I'm not so sure, but it looked like the right bundle branch block.
Yes, the QRS is wide. Okay, the PR is normal, so the PR distance is normal. The QRS is wide, and we do see a wide R wave in V1, okay, and an S wave in lead number 1 and V5, V6. So that's a right bundle branch block, okay. The axis is okay, and the AV is okay. So that's only a simple right bundle branch block, and complete because it's wider than 0.1 second. That's it, period. Next one.
I got 113.
113, okay, 113. Oops, wait a minute. 113, 13. Come on. 113. Come on. Yes, it's right here. Okay, good.
Yes. So first, this is arrhythmic.
Mm-hmm.
Lead 2 is equiphasic and AVL is positive. So the axis is around minus 30 degree.
Okay, good.
QRS is narrow.
Okay.
There are P waves, but some P waves, they are not conducted.
Okay.
That suggests second degree AV junction block.
Okay.
And then I counted the length of the RR interval.
You don't need to look at the RR interval if you do have an AV block. The RR interval is only an extra thing that you can use. It's enough if you're looking at the last conducted PR and compared to the first conducted PR. Are the same?
Yes.
So, what does it mean?
That's type 2,
Mobis type 2, exactly. Mobis type 2 second degree AV block. That's it. All right? Good. Very good. All right, next one. Nothing else? Okay, in that case,